Kang-Kuen until so please.
Okay, yeah, it's a great pleasure to be here. You know, I love Arizona. I love optical molecules. So where else can I be? Okay, so I guess we'll use one of this. So today I will kind of talk about the technology. So optical single molecules in optical tweezers. And in the pictures, you see, I guess whichever is easier. You see optical molecules in Chinese writing, but it's spelled out by small atoms on the top, right? And actually getting single particle is quite special. So let's just talk about this first. Actually, okay, here. So actually, I'm gonna broaden it up a little bit first because, you know, I'm in the chemistry department and I like to try to make some connections to other things that going on, which are also very interesting. So this is one of the Nobel Prize in chemistry. It actually in 2014 it was awarded to development of super resolved fluorescent microscopy, but it's really kind of two things together. It was single molecule spectroscopy and single molecule detection. And here I show you a picture from the work of my colleague. We didn't get the Nobel Prize, but that's fine in the future. Where you can see this image of, you know, there's two images, diffraction limited images versus this Thorn image, which is a single molecule detection technique. And basically, they're able to switch on, you know, fluorescence of molecules, single molecules, in kind of in a stochastic way, and then collect a lot of photons, and then sort of nail down like where the center of that isolate is. And then of course there's like a whole structure in fluorescence and there's many molecules, and then they can sort of piece together this image down at the bottom. And then of course you can see, like once you can in the molecular resolution, you can actually see the structure of a molecule. Yeah, it's usually like some kind of fluorescent tag onto molecule. But I think these are like green fluorescent photons. Much bigger than. It's just like a little light source. Okay, so I mean so like single molecules is actually a very big field in, you know, mostly in chemistry and connecting to biology, and of course, you know, we're taking inspiration also, you know, not just from atomic physics, but also from, you know, other areas. Okay, so what I want to see if this thing works. Okay, so optical tweezer is the keyword for today's for this lecture, and optical tweezer was invented by Art Ashton, who actually also got the Nobel Prize, kind of long overdue, and you know, he was 90 something and kind of right before he passed away. So this is actually quite science fiction because if you think about it, and you know, now we're kind of taking things for granted, but in the past, of course, you know, like this was first invented in the 1933. Actually, before that, he had already invented using light to trap things, but usually you have to, usually in the regime of sort of scattering forces, but not like a single beam trap until you have a very tightly focused beam. In this case, no. In the schematic, laser goes through a microscope objective and focus down, then you have those scattering forces and gradient forces, and the key is the gradient force to allow you to trap things that have polarizability. And this has been used actually a lot in biophysics. And you know, another picture on the left hand side is people like this picture and the work by before that they are able to match molecules with beads, and what they actually trap is also feature are the beads on the molecule, okay, the beads, and then they can, you know, they can measure mechanical forces on molecular motors. That's also very, very cool. And let's see, which is what? Oh, no. Okay, so what this is supposed to be is these are sort of nanosphere that trap in liquid. And you can drag them around with optical tweezers. And this was, this was a nice animation, unfortunately. Couldn't play right now. Actually, maybe I could try to play it with, no, never mind, that's not what, but, okay. So you can, just drag them. So basically optical technology combined with optical tweezer, you can manipulate more particles. Yes,
I wonder what laser use.
what laser frequency?
Yeah.
I'm not sure, it doesn't, my feeling is whatever laser power, where you have laser power.
I know that too. Right.
Yeah, these are in the
So the year is 2002, so I think the 1064 is already.
Yeah, I mean, but there's, okay, it's also, it is really five there. Right, but,
Ball has to be replaced, so they will do so after.
okay, and, okay, it's gonna be kind of hard. Okay, so then the key is that these are trapped in liquid, like, they're not being held against, I mean, in a way, they're not suspended against gravity, like, in the liquid, you kind of floating, and then you can manipulate it. So it's not as hard as having a single atom, I would say, right? I mean, this is sort of evolution of technology. And then, but then of course now we have these single atoms, having single atoms, these are animations made by solutions. And you can really sort of play with the single atoms to, your favorite example. And then the previous animation was supposed to be playing Tetris with those nano particles in the portion of things. Okay, so this is what we're going to talk about today. Actually, so and I changed the plug. The beginning part is going to follow this review that Anna Kaufman and I wrote, and it's relatively short review, so I recommend you read it. I like it. I don't write very long. I recently writing very long things, so I think it's just the right way. Okay, so getting single atoms is really challenging. Actually, I mean, nowadays not so challenging, but it's actually quite special because what I was just saying, in liquid, things are suspended, you can manipulate, you don't have to kind of hold it against gravity. But getting and then there's, as we'll probably discuss, getting single atoms is not so trivial. And this was first was done in 2001 in okay, so what we're seeing here, actually maybe I should just be here, and well, I can't really see my mouse. So okay, so what we're seeing here, actually, maybe do we have a stick so I can like hold it? Yeah, I'm not following. I don't think it's what. Okay, so anyway, what you can see is these, as okay, so the technology here is that the way people trap single atoms, and first time is to have a vacuum chamber, and there you can have an ensemble of laser cool atoms, will be an ensemble, and then the laser focus, usually sub-micron size, kind of overlapping with these laser cool ensemble, you may need an optical trap, then you can grab single atom out of it, and on the left hand side you see single atoms blinking in and out of this signal, like counts on camera versus time, and single atoms blinking in and out of these traps. Okay. And this is actually utilizing what's called a collisional blockade mechanism. Okay, so getting one is actually usually when you hold something, then I'll probably not feel that. And then of course in the trapping co-atoms and we usually don't deal with all that, but still we work with four, right? So even in the magnetic optical trap, we have on the order of a million atoms, and then to get one is quite special. So the mechanism to get one is actually this collisional blocking mechanism, which is a little bit illustrated in the picture with the potential well, is that there is a mechanism, and I'll tell a little bit more detail about the mechanism, such that if you happen to have several trapped in the well, then while you interrogate, then then you pairwisely eject out these atoms, so then you either left with one or zero. Okay, so how do we understand these mechanisms? I guess I'll use the book and looking at that particular potential that's drawn at the left bottom, the bottom of the left hand side. Okay, so first of all, you notice that I draw three potentials with different asymptotes, and the very, very bottom one is minus 1 over R6 potential, which is the van der Waals potential, and that's something I think has been talked a lot about. And that connects to the S, for example, think about an alkaline, and that connects to the S plus S. And so this is the molecular potential in the asymptote, limit, and the next one is the S plus P. So maybe I'll just draw here so that I can't point to them. So this is like energy versus internuclear separation. And then we have one that's like.
Sorry, could you use it?
Okay, yeah. In the asymptotic limit, we have minus 1 over 6. And then the next one, actually there's pairs of it. It goes as 1 over R3. Okay. So usually what happens is that you have these, cooling line on, and the atoms get, pairs of atoms, atoms get excited. To the, let's say, sorry, this is that. So go from the ground state, which here, go to here, okay, and then usually we detune in of them because we usually do laser cooling with resi tubing. So we detune a bit, and then that immediately you can think sort of classically that there is attractive force between the atoms, and then so it starts to sort of go this way, but after some short amount of time, it could decay back down to the ground state. Photons will decay out of the system and then back down to the ground state. And by that time, the atom pairs have gained enough kinetic energy, oftentimes exceeding the trap depth, and then it can get ejected out. So that's the process of ejecting pairwisely. And if you just have one atom, then you don't have such a process. It just sits there. So if there was 3, then 2 get ejected, and 1 is left behind. So this is the original blocking mechanism and the parity protection. So one thing I wanted to sort of diverge and talk a little bit over here is about these potential, because I think just to kind of segue into talking about dipole-dipole interaction, which will be talked a lot about today, and had been talked about in the past, but also today and the rest of this week. Okay, so does anyone know why down here we have a 1 over R6 potential, and up here we have a 1 over R3 potential? Yeah, so this is typically called a van der Waals interaction, and that's usually called the resonant dipole. And it actually has a relatively straightforward, it's actually relatively straightforward to kind of understand, and I think it's worth while to take a little bit of time to get into it. So let's think about dipole interaction. The dipole, for example, if we have dipole point in a particular direction with some kind of separation, I'll call this dipole V1 and that's V2. These are some kind of vector, which are the separation of charges between positive and negative. Then we know the dipole interaction is written as the following way, and we'll many other lectures will get into it a lot more direction. And then the second part is kind of it depends on sort of the orientation, relatively the dipole relative to the separate relative to the vector that pointed from one dipole to the other. So the dipole can also be pointing in like different direction, and then there is a vector going from one dipole to the other. Okay, so that's sort of in a property form. Okay, so now the important thing about so let's just kind of ignore this piece for now, just kind of think more qualitatively. In general, we have something like V1 dot V2, right? Okay. So if we think about the interaction of two atoms, and two atoms are like dipoles because they're not really point particle and has a positive charge in the middle and then electron. We can think of them as we can think that about their dipole. Okay. So if we have two atoms that are interacting and we're concerning two states, S and P, for example, ground in the center state of the two atoms. The way to talk about two atoms interacting is to go into the picture, not separated atoms, but together. And therefore, the energy diagram will be more like this: Eg, Be, and Eg, and E, right? So if I treat the whole thing as the whole system, then it's more natural to actually talk about an energy diagram that's in the following way. Okay. So these are separated by one distance r. Okay. So now, in order to evaluate sort of the dipole interaction of the two atoms, we know that the dipole transitions connect states of opposite parity, which has been talked a lot about in many lectures already. And therefore, we can see that in the state, so certain states here will be coupled due to the dipole interaction. In particular, these states will be coupled because they have opposite parity states, and with dipole moment of one and the other, they can be coupled. And then these will be coupled as well because G can go to E after the transition dipole, and E can go to G. Is that clear? Okay. So now if we assume that energy difference here is, we just write down some kind of this is omega naught, some characteristic energy difference, then the energy here are 0, h bar omega with one excitation, h bar omega naught, and 2 h bar omega naught. So if I want to evaluate the Hamiltonian for these dipole interaction of two atoms in the basis of Vg, E, Vg, yes, Vg and E, because those are going to couple, and Eg and Ve, then I can write down, I can evaluate their matrix elements with respect to this dipole interaction, and some basic energy difference due to the initial energy difference. Then we have something like in the following way, we have some, let's just say, G is P here. E square over R cube, E square, E square over R cube. Okay. And E and G and G and E also couple where their energy are both H bar omega, naught, and their coupling is again the following. Okay. So now we have a Hamiltonian that's actually has two blocks and we can deal with them separately. And this, as you can see that because these energy are the same, this is the resonant dipole. This is the resonant dipole situation. Okay, and the resonant dipole situation, you know, I can just also because these diagonal is the same, extended identity, I can just you know, say it's roughly, you know, I can simplify my 2 by 2 matrix to be the following way, and then we know the energy, eigenenergy of that is plus minus omega. Right? So the energy separation due to dipole-dipole interaction, because this is on resonance, these two terms have the same energy, then what I have here is d squared over R cube and minus d squared over R cube. And then these two, because they are not on resonance, because they're different by 2 h bar omega, again, this is the two-level system that we can write it like this way. And solving the 2 by 2 matrix, the diagonalized 2 by 2 matrix, you'll find that the energy of these are delta plus omega squared over delta and minus omega squared over delta. I think that's right. Let me just check that. Okay. Which my omega is reduced to square over R cube, and therefore this actually these states, so this is different. My delta here is the 2 h bar omega, so this one is going up again, like this whole thing squared, okay, over delta, which is 2 h bar omega naught, and this one is going down as R d squared R cubed square, and therefore this is proportional to 1 over R minus 1 over R six. And this one up here is 1 over R. Okay, so that's why I erased it. I already erased that picture, but that's why when I draw actually over there, now going back to my slide here, we have a van der Waals interaction, which goes as 1 over R six, and then we have resonant dipole coefficient. That's 1 over R. Okay. And then there's one state that I didn't draw, which will be B plus P, corresponding 1 over R. Okay. So this is important in a way that because in this case we're considering homonuclear molecules, so these two atoms are exactly the same, and therefore the 1 over R six and 1 over R cubed is actually quite different. You know, the eschaton is very different. So very quickly it gets energy. And this is not a case if you have two different atoms, for example, sodium cesium or rubidium cesium or KRB. Like if you have these two different atoms, then you have 1 over R6 still here in the S plus S and S plus P here. What would you think we would have? in the S plus matrix for the deuteranuclear molecule, or deuteranuclear atom there. What's that? Why is that? Right, so it's not on resonance, right? So that this is also, I guess, one of ours. So in that case, if you have two different atoms, they will still absorb photon and get accelerated, but it will take a lot more photon, as compared to the homonuclear. So this is actually kind of a key, aspect of trapping single atom because we have these parity projection. Okay, so therefore the stochastic loading you and I think is around then, and that's typically true, but it turns out for not a very, not completely cool down to the ground state kind of acid, not very cold. These are cool atoms are not often super cold. They can still have some individually kinetic energy, and therefore even together. You can imagine that they're getting the energy to try to get ejected out. But one is already moving this way, so in the laboratory, right, it could be that one get ejected out, but the other one is not, because they're already moving. Does that make sense? So then empirically, and people done Monte Carlo simulation seems to suggest that actually about. These are not very cold. Okay. So that's actually being utilized to both in atom and alkaline atoms nowadays, and also molecules, basic movable molecules. So this is one way, actually relatively easy way, I would say now, now it's been shown in many systems, to get single atoms, and other ways of getting single atoms are technically a lot harder. For example, you get much colder, you go through some kind of quantum transition, for example. Or emergency power. And I guess just to finish my so other techniques is one quarter, and then to really get one atom or one particle out of ensemble is not so. So like one idea is like, well, I don't want to have 50%, I want 100%. How do we so like this, getting to 50% seems to be very easy, getting to 100%. Okay, so you can't see my next slide. What should we do? Yeah, I think the power must went out. Yeah. Also. Yeah, I mean, it seems like the emergency. It's the emergency lighting.
Well, this triggered.
No, we're not.
Somebody's missing. Oh my God, where's the second? One of us said the bird. Seriously, you're really not being here.
I deserve it.
No, you didn't.
I was hoping you may go into more detail.
I will, yeah.
Yes, yes,
Yeah.
that's.
But
what
you
I-
really set the stage.
Yeah.
Yeah, yeah.
Okay, we just continue then.
I think so, but then apparently the wind is sort of along through our poles, so it's just not happen again.
Yes.
Okay. For now.
Okay. Yeah, so and you know, like, well, and this, okay, so, okay, so getting 50% is now, you know, there's mechanism you can have such a mechanism in the system. Getting to 100% is harder, so there's many ways, one is going about this, and some of the ways we want to pull in the future, not having to the ideas and stuff. Okay, so one way to get closer to 50%, it turns out there's this enhanced loading mechanism that was demonstrated first in New Zealand group, Chicago, and where they say, okay, instead of using the ready tune, you know, and then so and you know, so you come in the uncontrolled way for the atoms to collide and get in kinetic energy to get ejected out, they go Bluetooth, and when you go Bluetooth, you know exactly how much energy you give it before it reaches and come back out again. Okay, so they go Bluetooth, and that goes through this one, you know, the upper branch, and then they show me data shown on the left bottom that in Bluetooth case they were able to get the way you will read these plots is that you repeat these kind of experiments many times, and then you collect those on your camera, and you see, you know, a point which usually corresponds to the lowest one is no elements, and then the first one is single, and then one collaborated, and then finally you guys will over to that. Okay. So then you can see that this bomb is now a lot bigger than it used to be. In particular, they have used. But when this was first demonstrated, which was great, but it was done at the sacrifice of, you know, you had to have a lot deeper optical freezer tracks. But it seems then, the original group had shown that you could go to a different Ruby tune state, a different excited state, actually, this case in the alpha. They choose the P 1.5 state, coupled together with when the enhanced great molecular cooling and even a large array, even they can have, you know, relatively low track depth, much less weight than 6 times less, I think. Then they can, you know, you can get higher loading and still in a more scalable way. And that has been demonstrated for Rubinian sodium and Urbium. Okay. So now we're getting closer to 100%, but not quite. I mean, this is actually a very important step because not everyone uses it yet, but you know, a lot of experiments are implementing them because you know there's still a big difference when you try to scale up between 60% and 90%. Each one has that probability, and if you want 100% fill array, then you need work a lot harder. Okay, so let's see. Now you can also mitigate. Okay, so then to get to 100%, then one way to do it is to mitigate where there's holes by simply eliminate them and fill with that. Okay, so this is the approach, and on the left hand side, I show you a typical. There's sort of two flavor. Actually, perhaps we can. Okay, so there's sort of two flavor. One is if you do one-dimensional, array, then you have usually these acoustic optical reflector showing this picture label B on top, transformed. You see lots of holes, and then you can illuminate those holes. You take an image, eliminate those holes by reconfigure your acoustic optical reflector frequency to move them so that you're compacted up to this array down here. Okay, but then to go to 2 dimension, the way people shown, and that was the thing to look at, and to show, in 2 dimensions, people use, for example, in drawings, or demonstrated, you start with 2 overlapping tracks, so a track that's, underlying track, which is done by spatial light modulator to the patterns you want, and then you overlap it with cross ALD, so acoustic optical detector that can put in both X and Y, let's say, and then you overlap them, and you can move the acoustic optical detector, which can, change much faster than the special light modulator, and then you can have a deeper track and drag them from one place to the other. And there's 2 types of moving that they show in the picture, in the picture, where you can move in between the elements or in between the design track, or you can move along the grid of those tracks. And it seems like the type 2 move shown over there is a little bit more robust. The other one is like if you get close to 2 atoms, you might also pick out the atoms nearby. So those are sort of the realistic practical constraints. And in order to go for even more exotic geometry, oftentimes you map the picture onto a grid. You kind of say like, you kind of map the geometry onto a grid and then sort your atoms using the algorithm that you would implement for a grid. Okay, so that's one kind of entropy to mitigate, and the other kind of entropy to mitigate is that these atoms that are in the track are often only laser cooled, so they're not so cold yet. They're not the coldest possible particles yet. So in order to get them into the motional ground state or the track ground state, you do something like a sideband cooling. You need to resolve the motion. And then in this particular work or illustration, what you can see is the way to do these sideband cooling is that you start with potential. These are the energy difference between them are their for example, alkaline atom, their hyperfine energy. So the potential looks almost the same, and then you can resolve the motional spacing, motional degrees of freedom of the atom, and then you drive transition that couples the motional degrees of freedom, and then reset the internal state by all. And then you iterate that many times until you do a spectroscopy something like this. You can scan the frequency, before you cool, for example, you can scan the frequency, you can see bunch of sidebands, and then you can, first go to a side, second, third, well, actually, if you start out any pairs, and then you go down and go up, so it's like, this quantum population is not only in the ground state, but when you drive it, you add one when you lower one. Okay, and then you can sometimes either take this is like custodian, you can even drive multiple cycles. You can drive multiple higher orders, and then so you can sometimes do larger number of the complex. That's very important. And then once you pull, eventually you see these are all gone because they're mostly on the ground state, and therefore the sideband you just couldn't go down and more because you reach the limit of that potential. You couldn't go down. So the asymmetry between these side, the radius side tells you the ground state population. Okay, so with this one can also do sort of 90 something percent to the motional ground state. Okay, so then beyond that, if we want to start to have these particles interact, so this is just kind of generic thing. You can have them collide, you can use Rydberg interaction, you can use electric or magnetic dipole, and of course we're interested in the electric dipole moment for the spectrum for molecule, and for ions you can do motions. Okay, so with that, I'm gonna go into my introductions. Just very briefly, we talked, there's many lectures already, so just to kind of summarize, the lots of different directions that we're interested with molecules in terms of the relevant many body is that the precision measurement usually concerns a lot of, the molecular structure that gives you what you want, the instant of sensitivity to physically understand the model. So you often don't want anything beyond, particles. Like actually it's bad for systematic and stuff like that. For quantum simulation, quantum information processing, we like to have the control over the two-body interaction and then sort of scale up to many bodies. Usually start with two bodies. And for chemistry, also chemistry usually concerned with collisions, how collision of two particle or three particle, how they turn into one another. So that's sort of the general separation of how many body physics that you care about. And what I'm going to talk about, already started today, and the next lecture is going to concern more in the area of simulation and information processing with using molecules, and the final lecture will likely be on the ultracold chemistry. I haven't fully decided. Okay, so okay, so this, of course, there's many other technology and, perhaps much more advanced at this point, to pursue these directions. And I was, some example here, and then the important thing is that all of these systems and the basic requirements is that we want to have them fully controllable, both in terms of its quantum state, but also individually. We need to be able to scale up, and we need to allow them to interact, obviously. But despite a lot of progress, I would say, a major challenge remains to have very high fidelity entangling or interaction, but very high fidelity interaction in a scalable way. And that's where I think molecules could potentially wins, but of course we have to show it. And because really harnessing the complexity of molecules, and this is utilizing the internal degrees of freedom, which are generally coherent already, and then these tunable dipole interactions are also an intrinsic interaction that is not mediated by external fields. It doesn't have to be mediated by external fields. And of course, that dipole-dipole interaction, as I already alluded to, and John is going to talk more about it. Give us more theoretical background on that. The prerequisite from experiment point of view is that we need to cool and trap and what did I say? Quantum state control there. Okay, so let me just skip this examples, and Simon is going to talk about how great the molecular qubits are in terms of our coherence. Let me just talk about what I really want to talk about today. Is the molecules in optical tweezer. I'm using, there are sort of two complementary approaches, and I'm focusing on one. Okay, so the two complementary approaches are, let me just go in here directly, is to directly, let me just show directly here. Directly laser cool molecules, and you can grab individual molecules out of an ensemble, illustrated in this nice picture that I'll in the review, and then or we can assemble directly from single atom. Okay, so this is compare and contrast, because our goal ultimately is to get to the molecule to be in the low vibrational ground state or in the vibrational ground state. And we need a notion of ground state. So on the left-hand side, this approach is very good in terms of either grabbing a single particle, single molecule, and you can see a picture of that. But these optical, these electronic laser cool, which the couple had talked about the physics behind it, definitely a molecule. We can fluoresce and then see these individual molecules, but their states are often scrambling lots of different ones until you do optical pumping and you do some state purification. Okay, so that's what this second step is for for most of the applications, they're interested in staying in a particular content state, and then we had to do the additional step of purifying that and stuff, and usually involve the optical company. How efficient that is depends on, complicated molecules. And these are still relatively, although they're already, useful for, and to really get to the motion of ground state, while we're having dimensionally on the molecule, and that's working properly. While this assembling technique on the right hand side, you can track and cool, we already showed you data from the atomic physics toolbox. We can track individual atoms, we can cool them to the motion of ground state. And it turns out this cooling is a prerequisite to make molecules. So that's not only it's not this nice to have, but it's actually necessary to have. Okay, so we trap and cool, and then we have to put them in the same trap so that they can actually have a chance to align and make a molecule, and then we utilize quantum state manipulation of molecular association. Talk about association, and then so to bind them into molecule and subsequently put them into from these kind of still far away atoms, but in the molecule, special molecule, to these tiny ground molecule and the low vibration constant. And the nice thing of this technique is that because ground state cooling of the atom was necessary, and I'll elaborate that in a bit, that means molecule ultimately, once you make a molecule, they're mostly okay, so so I still have some time. Okay, so I will focus on, and I'd be happy to answer any question in terms of compare and contrast, but I prepare mostly about the technique on the right-hand side because that's what we do in my lab. Okay, so let me just now talk a little bit more about this. So the difference, I guess, between what I have told you about having single atom to this making molecule is that we actually need two different atoms. And that turns into, it's not twice as hard, not twice as hard, but like maybe quadratic, maybe scale is quadratic. So we need two different colors to manipulate the two different atoms. So we tell these are the different colors, we chose for cesium, so in other words, sodium, in this example, we sodium and cesium atoms because sodium cesium atom ultimately has a very large dipole moment, 4.65 or 4. Whatever, but that is one of the largest bialdehyde combinations. And I would say like the very largest the largest type of moment of the molecule is probably on the order of 10 device, so we're not that far. We only have to understand that. Plus we get to work with alpha and we kind of know how to do it. Okay, so we overlap with all of these and we can image the individual atoms and overlap it with the laser pool ensemble of sodium and cesium, and we can take image of this. And these are sort of, these are stochastic process, like I explained before. So only fraction of the time that we have both the sodium and cesium loaded in the same shot. These are sequential images. And these are exactly sort of histogram that I was talking. Okay, so for the experiment, oftentimes these three are all useful because you can say this is the process that involves both atoms, and this is the process that involves only one of the atoms. So it's like a good controlled experiment. Of course, it's not useful in loading atoms. But you can post select on these sequence in a sense that you take an image and then to see what you have loaded, even though it's stochastic, and then you proceed with your experiment and you see what happened at the end, you take an image to do your analysis. Okay, so of course we need to do, to do better, we need better starting point for making molecule. We have to do rearrangement like I explained to you. So this is the one-dimensional case where you start with some distribution over the different traps, and then you eliminate the ones that are empty by and then compact up the traps. Here is just to show that, you know, initially we have indeed these kind of 63%, I would say. That 60%, you know, along all the traps, we feed in down here, we have 16 traps, and then we can eliminate this one and move the one that still needs the right hand side. Okay, so that's trapping atom, and then we do cooling, which I'm not going to elaborate more beyond that. And then the next step is to merge them, and it's physically just sort of tuning the potential of the trap by changing the intensity and changing the steering of the beam orientation, and overlap the two atoms onto the same spot, and then eliminate one of them, and both of the atoms are trapped in the same optical tweezers. And this can be done. I'm showing this picture especially to my students. This can be done without heating, and you can see that in this work we do this thermometry where in this, well, this is no merge and this is merge. Initially, we're already moved down to the ground state. The sideband is eliminated over here from both axial and radial, and if we do the full merge sequence, you know, it's still basically no. So this can be done completely in, you know, the ground state, like the atom state in the motional ground state, moving in and out. Okay. So now with two atoms in the same trap. Yes, question.
Can you do sideband cooling with, you know, one sodium and one sodium atom in the same trap?
No, it's hard. So it's kind of what I was kind of alluding to. So that would be this case. So you could probably cycle photons a little bit, but then still very quickly you want to run this process. It's better than 1/2, but it's better than if you just have a single species. But in terms of pairwise infection, but it's not practical. So that's why we separate them, you know, to do the cooling, and then we merge them, kind of go through this trouble. But perhaps there's, you know, that was just the idea that was just the way that I can think of, you know, perhaps there's better ideas, you know, so. Okay, so now we have two atoms, then the collision of two atoms, it turns out nothing will happen. And oh, this is too fast. Does anyone know why? You collide and you don't make a molecule. Yes.
Why the energy can't go anywhere?
Yeah, exactly. So you have.
We had a conversation on that.
Oh, yeah. Oh, okay. Yeah, so exactly. So like collision usually takes 3 particles. Okay. So 2 particles turns out colliding, nothing really happens because we need to simultaneously fulfill conservation of energy and momentum. And if you try to make a molecule eliminate that binding energy, there's no place to go. Okay. So in order to make a molecule, everybody get that point? Okay, and in order to make a molecule, we need additional stimulated field using light or magnetic, and that's indeed what we do. Okay, so that's just sort of a caveat with 2 atoms. So, now, to make a molecule out of 2 atoms is still very challenging, you know, even with the addition of the field, and the reason is really a wave function mismatch, and simply put, you know, the atom we can, you know, we have 2 atoms, both have some uncertainty, you know, in terms of its location in the trap. The best case scenario is to cool the atom to the ground state, and then maybe, you know, 50 nanometer, you know, wave function spread in 2 dimensions, in the worst dimension, and then maybe a little bit tighter in the tighter dimension. But you have to, like, that's 3 dimension and 2 different atoms. So if you know, integrate the wave function overlap between that scenario versus the molecule on the left-hand side where the 2 atoms are exactly the point that 2 nanometer apart, then that overlap is 10 to the -8. Okay, so it's very difficult because of this wave function overlap, and that binding energy has to also go somewhere else, and that usually corresponds to a large amount of energy. Okay, but the solution is, and I think Simon will elaborate more. has been realized in many labs, is to bind them first to some special resonance, scattering resonance, to weakly bound molecule states, to prepare them in a single quantum state, and subsequently coherently transfer them from one. So these are the illustration. Transfer them from one state to a target state. And then because we kind of already eliminated entropy in the sense of preparing them in a single quantum state, so then even though this is a very challenging technique, challenging steps, very low wave function, it can be done very well because it's a quantum state transfer from one to the other. So essentially, it could be 100%, if you do everything right. Okay, so all right, just right before. Okay, let's see. Okay, so I guess I'll talk until my computer dies here. The punchline here is that from exactly 2 atoms, we can make a molecule with 30–40% efficiency. And you might wonder why. Well, first you should be in awe, this is actually quite efficient compared to 10 to the -8, but then you may still say, like, why is it not 100%? So so that's a fair point. Then you can think about how to make molecules from 2 atoms. This is actually, you have to think in turning the 2-body problem into one. Always doing quantum mechanics to make the problem simpler. And so on the top, we have this 2-body Hamiltonian, and on the bottom, we write it in terms of center of mass and the relative coordinate of the 2 particles. And if they have the same trap frequency, which in our case is about 10% different, then you can, the last mixing term is actually 0. Like the problem will be exactly separable. But in reality, they are slightly different because they're not exactly the same atom, and then you can tune it with wavelength, but it may not be where you want it or where you have a convenient laser wavelength. But it's a small difference in terms of trap frequency between the two. Now, the efficiency turns out is best illustrated in this picture, which are work in the bulk gas from a while ago now. John, are you on that? No. Oh, you're not. There's like everybody. Anyway, So the important thing is that, like even in the bulk gas, you can think about this quantized level, or functional level. And the one that actually, the separated atom actually connects to one, the bound state to a fresh spot resonance is actually the one that's in the most contrast state. Okay, so these actually connect like this. The important thing in the bulk gas, we talk about phase density, and the colder of the gas, you have the higher phase density. And it is because of this picture on the right, that only the ones that are already, so as you can see that the limitation of how well we can convert into the molecule with 2 atoms is how well we can mostly cool all the degrees of freedom so that it's graphic, and then we are about it to move them around into the center and still maintain it. So that's sort of the limitation. Like if we can get their population completely in the ground state, then we can convert to 100%. Okay. Right. Okay. So not gonna worry about that. Yeah. So in the bulk gas, that efficiency is usually 15% because I guess indeed I could say a little bit 15 to 20% because there's lots of competing factors, and therefore you can't get as cold because then you have large two-body loss and so on. So for 2 atoms, if you can get them into the motional ground state completely, then you can be better. And then in fact, we show that we could be better, but of course we're still far from 100%. Okay. So let me just say that if we map the motional ground state atoms into, to, the special molecule that has no rotation excitation, we can also map with motional excitation in a control motional excitation, for example, put one motional contact and then map into special molecule that has one angle moment, right? Like this you can essentially you can play around with these, mapping the two particle motional degrees of freedom to the molecular degrees of freedom. Okay, so without going too much detail, like in an experiment that we've done in my lab, where we can purposely put one motional contact after cooling down to the ground state, put one motional contact to one degree of freedom, and in this case, medium, so that translates more to the motional, to the relative motion, because the heavier particle compared to the sodium, the lighter one. Then you can connect to a P-wave Feshbach resonance, which has 1 unit of angular momentum. Okay, so let me just oops. Let me just maybe say here that so it turns out if you go to the math, then most, you want it to be here in the sense that all that around it. And basically, the rows the most around it and the center of that. But in reality, you can be different. And so on and so forth. So you could have molecules, you have to point that most one is with a zero, but in the center of that point, it has some expectation. So one can do the thermometry to figure out, how much rapid population we have using
Where do these expectations come from?
they are just coming from the fact that I believe it's just that they're not perfectly grounded. So they
Temperature.
yeah, exactly. So but somehow but still they can be in the wrong grounded. That mapping. The mapping can occur. And therefore, in our case, not perfect grounded full, but a little bit of excitation in these equivalent states, yes, you're all turning to molecules. So our molecules are not 100% emotional ground state. They're, I guess, by this thermometry, about 75%. Yeah.
Why the temperature would affect the motion was not very
It's just that these are not turning into molecules. So I'm concerning the population, the molecule that are created, how much of them are in the ground state. So it's not 100%, even though it's close to, I wanted to say it's close to 100%, but we can do a thermometry to say how much. Okay, so computer is crashing a little. Okay, my computer is crashed. It's stuck there. It's a rough time anyway, so I don't know. It's running too many things, maybe. It's stuck here. It's stuck here. So yeah, I know. I tried to do the next, and then it's like the mouse is spinning. I tried to do the next page, and the mouse spinning. Yeah, so I guess I wanted to give the punchline is that it's just let me just if I can get to it, so I remember what's on my slide. The punchline is that by controlling the individual atom and mapping all that control onto the molecule, this technique allows us to have molecules in an array. I remember the next slide, but this is the rationale, like all these mapping of atoms, internal degrees of freedom to molecules is done on the Feshbach association step. So these molecules are whole, mostly ones that are thick, and in turns out internal degrees of freedom here we do a two-photon, we do a two-photon excite, we do a two-photon transfer all the way down to the low vibrational ground state. And those are, basically ready for us to allow them to start to interact once we put it. So, yeah, we do additional work. So I guess I'll just end here. Okay, yeah, I'd be happy to answer the questions.
Questions?
Yes,
So, at the very, just now you said that mapping between from atoms to the molecule have this F-block association. So if you, depending on which F-block resonance you use, will that map to different center of mass versus relative coordinates? Like that, your atoms have a certain temperature, like, but then you can choose to map that into relative or center of mass. Did I understand that correctly, or?
no, I mean, well, I mean, yes, a little bit, yeah, so like, but usually the degrees of freedom that you map, you know, so, motional degrees of freedom are mapped into rotation and vibration. And then center of mass is still sort of separate. So usually you don't have too many choices, like my Fishbach resonance are resonance that has a specific angular momentum, so you can play around with, like, if you want to go use an exploit Fishbach resonance so that there is no angular momentum at the resulting molecule, then you want to start with motional mass data. And then if you go to, use a P-wave resonance that I showed you, then you want to impart a motional excitation. And also in terms of choice, you will want to impart that. You can only control the atom, I think, could probably control them together, but that's more complicated. And then the one atom that you decided, if we chose the heavier one, because that goes into the relative quotient more significantly compared to the lighter one. So if we excite the sodium, then it won't convert as well to this way. Like, it won't have the right kind of character to start with and get converted to the way. Yeah.
Is this a correct statement to make that conversion efficiency to a molecule is better if you have the graphing frequency of the two atoms as you go?
That's not necessary. Not necessary. I mean, the math is not as important, but I think you can still math then correctly.
So if not, then